Okay, so we're rolling here. So let's review here. So above is a picture of a rectangular region whose length is growing. The rectangle, so let's think about this. The rectangle's area grows at a something of, and then this is a value with respect to its length, which means that what? So if we're saying it's growing, we're saying it's growing at a, what fills in the blanks here? What's the key concept here that this is talking about?
At a rate.
Right? Rate of change. And what is the rate of change for this growing area?
A constant rate?
Yeah, what? Yeah, and this is actually asking for the value.
Okay, 4.
Yep, 4. So, sorry, this is a little small here. This is 2, it's 4. Yep. So it's 4 inches, or whatever units squared per length. And what does it mean that the rate of change is 4? So this is something we started working on from day 1, and this is a really important concept of the course. What does it mean that the rate of change is 4? Anybody? I'll get you started. Given what? It means that given
like a change in x, the change in the y value will be 4.
So given any change in x, say dx, the resulting change in she said the resulting change in y will be 4. Do we agree with that?
4 dx.
I would say 4 times the variation.
Okay, 4 times dx. And what the resulting change in what? In y?
Area.
Area, right? The resulting change in area. And we could say d area equals, and then many of you said 4 times dx. So yeah, d area equals 4 times dx. So whatever change in x we see here, the change in area, the net change, or the new amount of area added on, will be 4 times that dx, right? That's just base times height, right? Base times height. Right, and that comes from the fact that we saw that the function value, right, this height, that is the rate of change. That is the rate of change. Okay, so how about this one? So now we have a variable function f. So any questions on that? So when you have a constant function, and this is where it all started, right? We looked at a constant function, and so we said given any change in x dx, the change in area is going to be 4 times that change in x. 4 is the rate, or the height, right? The value of the function. Okay, so what about for a changing function then? So this region grows at, again, a rate of change of what? What's the value of the rate of change now?
F of x.
Right, the rate of change is the value of the function, which means that given any change in x, what can we say?
There will be a different change in y.
Okay. So are we talking about y here? What quantity we want to talk about here?
D area.
Yeah, the change in area will be what? How would we get the corresponding change in area? Right, f of x times dx. Okay, so what do we think of this? Is this right? In spirit, in general, yes, but there's a problem with this. Does anyone see how we need to make kind of a new condition or a caveat on this compared to what we had before? There's a change.
Do you include the current interval? Or does it have to do...
Okay, yeah, you're kind of on the right track there. So we're imagining super small intervals, right? We're imagining super small intervals. And we're in the current interval, the value of the function is f of x. It's like a teeny little step at that function value. The problem is here. What's the problem with this, given any change in x?
A constant change in x?
Can I choose a change in x like this?
That would be too big of an interval.
And what's going to happen? Will our f of x dx be too big or too small?
Too big.
No, so
Yeah.
too small, right? So f of x would be this value, and if I choose my dx to be like, what is this, like a half or something? Then the resulting change in area I'm going to get is this. Do you see that that's not accurate? What change in area do I need to get? I need to get this,
Yeah, you're missing that top part.
Yeah, I'm missing this whole thing. So this doesn't really work anymore, right? With a function changing changing value of the function, the rate is continually changing. So how do I need to qualify this?
Do you need like a small set change in x?
Yeah, so this is only going to work for a small change in x now. If you take a change in x that's not small, then you're going to be increasing your area at a constant rate when it's not. It's increasing at a changing rate, right? So it works only for a small change in x where we're assuming that that function value stays constant for a little change in x. Does it make sense? It's not for any change in x anymore. That only works when that function value is constant. When that function value is changing, well, then the rate's continually changing. And to talk about what the rate means, it's only going to work to give us a small change in area for a small change in x. But the principle is still holds. It's just that dx now needs to be small, or else the rate's going to change, and then our change in area won't be accurate, right? So if dx isn't small, then that rate will change over the course of our dx, and this using the principle of a constant rate will not work.
What constitutes a small dx?
Right, small. So then remember, it goes back to what we talked about a week ago, like small enough so that we can't tell the difference anymore, right? So we looked at
Okay, gotcha.
totaling
Yeah,
up the accumulation. Remember that? Yeah. So we were working on building the accumulation function, and we kept looking at the approximations, and we said, okay, they're not changing anymore. It's like making it any smaller doesn't, for practical purposes, doesn't change anything. So we're done. So we know it's not small, right? So from 1/2 would not be small. So what about 1/10? Probably still not small enough, right? 1/10. 1/100th. Okay, now we're getting close. 1/1000th, probably fine in this scenario. Okay, so let's take a look at. Okay, and so this is showing starting from x equals 1 here. I'm increasing x, and I'm sweeping out the region between f, very slowly, sweeping out the region between f and the x-axis. So I have this function here. Capital F of x equals the integral from 1 to x of little f of t dt. And so what does that function mean and do? What does that function mean? What does it do? What is its function? So I'm saying capital F is the integral from 1 to x of little f. And I'm showing you this animation of this region. That's a little better, okay? So what is the function f? And hopefully you're thinking that the function f is?
Is it the exact net accumulation?
Of what? So of what? Good. Of what quantity? Since the
Function t, or f of t.
So it's the accumulation of function f. What do we think? It's the accumulation of these function values.
Of the area.
Okay, is that different? Are you changing your answer? So accumulating the function values and accumulating the area of the region, same or different?
The area of the region is always positive.
Okay, so it's the exact net accumulation of, so this is our area function, right? Because wow, I can't get it to stop jumping. Exact net accumulation of the and what area is it? So it's the area, what, between function
f of t and the x-axis.
Good. Function f and the x-axis. Because what's our rate of change here? What's the rate of change in this accumulation function?
F of t.
F of t is the rate of change, and we know when that you choose the rate of change to be the function value, the accumulation function that you're talking about is the quantity of area. Okay, so let's take a look at this. So what is what's the rate of change? Here's this say 1.4. Here's x equals 1.4. What's the rate of change when x equals 1.4? The rate of change of area.
Six.
About 6. Good. So it's the y value, right? It's the value of the function. So when x equals 1.4, f of 1.4, which is about 6. Okay? And here's 1.8. What's the rate of change of area now?
It's like 3.
Yeah, and so it's f of 1.8 is our rate of change. It's how, at what rate this green region is growing, and that's about 3. Okay, what about let's do 2.3? So what about at x equals 2.3? Rate of change is f of 2.3, which is about what?
-6.
Yeah, let's see. Sure, -6, about -6. So what does it mean that the rate is negative? What will it mean for accumulation when the rate is negative?
The accumulation will begin to like decrease in value.
Yeah, so this function will be decreasing. Whenever the rate is negative, won't this function be decreasing? And where does that occur? So that occurs this whole second part, starting at 2 to 3. This function that we said was the area function will actually decrease this whole way because the rate is negative. So then the question is this really the net accumulation of area? Are we really accumulating area along here? Or do we have to maybe make a little qualification? Maybe have to change it up a little bit. So what's happening here?
Accumulating the changes in area?
Yeah, so are we accumulating area here? What's happening to the function capital F? Increasing or decreasing?
Increasing.
Yeah, the rate is positive, right? Since the rate is positive, that's this function value. This area, the function value F is increasing. And what's it? It's accumulating this green area, right? But when we get to 2, what starts happening to function capital F?
It starts decreasing.
It starts decreasing because the rate is negative. Right now, this is, say, F of 1.3, capital F. Is capital F of 1.3, is it positive or negative? Capital F of 1.3.
Are you just asking in the interval from 1 to 3?
No, at 1.3. So this where I've paused it here. So capital F of 1.3.
It would be positive.
Positive. Why positive?
Because the area doesn't cancel out. Yeah.
Right, exactly. So we had all this accumulation of area, which is positive value, and now we start subtracting from that. But this amount of area is less than this, so our F of 1.3 would still be positive. So what is this really finding? This capital F function is really kind of like finding like a difference of areas. Wherever the function is positive and the rate is positive, that's going to have a positive contribution to this quantity, right? And then whenever the function is negative, that the accumulation in those values of x will bring this down, will make this decrease. So when do you think, for what x value will this come back down to 0 about? What would you say? So capital F is going to be 0.
Like 2.6, 2.7.
Yeah, maybe somewhere in here. Yeah, maybe somewhere, just guessing. Those look about the same amount now? So now the amount of positive contribution, and then we had all this negative contribution. I'm trying to kind of guess that now this gray area is the same as the green area. So now the value of capital F is about 0. And then what happens to capital F? Now what's the value of capital F?
Less than 0.
Yeah, so now this function, which we said was area, but it's not area anymore. Why? Because now it's less than 0, and there was a point there where it was 0. So it's not really area, right? It's not really area. And so now it's less than 0 and decreasing, right? So it's getting more negative. As we keep accumulating area below the x-axis, the value of this function is negative and getting more negative. Decreasing and getting more negative. So this isn't right. So this exact net accumulation is not area. It's not the area between the function and the x-axis. Okay. So we want to qualify that, and we're going to call this idea of difference of areas, right? It's a difference of areas. We're going to get all the areas above the x-axis minus all the areas below, and we're going to call that signed area. So when we choose the rate just to be the function value, we have to make accommodation for that function value could be negative, and that accumulation function will go down, right? Well, that's not true about area. Area would always go up. As we would accumulate an area, would keep getting greater and greater positive. So to accommodate for this, we're going to call this function, it's not area, but signed area. So signed area can be positive, it can be 0, it can be negative, depending on the combination of regions that we have above and below the x-axis. So the function f is the exact net accumulation of signed area between the function f and the x-axis. What does that mean? Anywhere that our little f rate of change is positive, we're going to be adding on area or adding on signed area to the accumulation function. Wherever that little f dips below the x-axis, we'll be subtracting off, or the value will be going down. We'll be subtracting off the amount of the area below the x-axis. Okay, does that make sense? So let's do a little practice exercise. Yeah, go ahead.
I'm sorry, I just have one question. So even if the area accumulated is positive, we would still call it the signed area.
Yeah, if you're using the function f as the rate.
Mm-hmm.
So yeah, if your function is always positive, then you can say that the signed area is the same as the actual area.
Okay.
Because you never have a contribution. But it's,
right.
it's you never have a negative contribution where the rate goes negative. Okay, so here are some functions, p and q, and I want you to watch this. So looking at the values as x increases, right? So the current value of x and the current value of the function are shown by the edge of this region, and the arrow shows the function value. So I want you to kind of, looking at as the numbers change, figure out what functions are these. What is p and what is q by looking at these.
Can I say, or are we gonna wait?
Let's just give a moment for people to think about it. So let's watch p together. So p right now is so it started at 0. It's increasing, and so then we write a relationship. And so now p is decreasing, right? 3, 2, 1. It's 0 now, and now it's turned negative. So what is p?
A function s, like lowercase s.
Yep. P is just another way of naming the f. And what is that relative to the situation about area? What is p then?
The rate.
Rate of change.
Rate of change, right? Rate of change. Good. Okay. What about q? So now q is increasing. Here it's 4, or 3.6. And now it's going down. It's 3. It's 2. It's 1. 0. Now negative and getting more negative. So it starts at 0. It increased this whole way.
Is it? Net
The accumulated area.
Is it accumulated area? So now here, look, it's decreasing.
Like mine, it's the signed area.
Yeah. So do you see now it's about to be 0, like we guessed, and now it's negative and getting more negative. So what would a relationship between p and q be? Could we write a mathematical statement that brings p and q together? What would we write?
Q of n equals.
So n is the current value. So we want to write a function for all values.
So x.
Okay.
Q of x.
Q of x.
Equals the net exact net accumulation. So the integral sign
Integral
from 1 to 3.
from 1 to 3.
And then p of n. Then dn.
Sure, we could use n. I'm going to use t because we usually use t, but n would be fine. Okay, what do we think? Do we agree with that?
Yes. Actually, I'd probably change the 3 to an x, but I don't know.
So what is the integral from 1 to 3? What would that be? Does that give us the accumulation of signed area at any value of x?
No.
Just one value.
It just gives you the difference of these two areas when we're all finished, right? So integral from 1 to 3 would be this. It would be negative 2.7. It would be all this area, all this area minus all this area. But we want the function. We want to get the net accumulation for any value of x.
Make it easier to x.
So it's x instead of 3.
Right. So we start accumulating from 1. And so now this function, given some value of x, like for instance, this is 2.76. So this function, q of 2.76, would be negative 1.4. Or all this green area minus all this gray area. Likewise, q of 1.76 would be 3.2. So we need that to be x. If we just put 3, then we just get like the accumulated signed area when x is 3, just one value. But we want the function for all of them. Does it make sense?
I just have a question.
Sure.
Could we have put it from 0 to, like, the integral from 0 to x instead of 1 to x?
Well, it wouldn't, maybe, it wouldn't, just wouldn't match with my animation though. Right? So my
Okay.
do you see my animation starting at x equals 1?
Yes.
Does that make sense?
Okay, I see. Yes, thank you.
And actually, no, so actually we couldn't, because if we put 0, then these values would be all different. So the q is necessarily 0 at x equals 1, and then maximum when x equals 2, and then starts decreasing from there. And if you did 0, you'd have a whole different set of signed areas because of all this. Does that make sense?
Okay, I see. Yes.
In fact, if you did 0 to x, q would always be negative, right? It would be negative, and it would increase, but it wouldn't increase enough, and it would still be negative at 2, and then it would get more negative again. So it would be,
Yeah, that makes sense.
it's a different function, right? So you can't put 0 there, you got to put 1.
Thank you.
Yeah, sure. Okay, so I got the same exercise again. Let's look at these. So we said P was the same as F, so I'm showing those. P and F are the same, but now I have two new functions, G and H, and I want you to figure out what these are. Here we go. So let's watch G first. So G is not registering anything yet. So we're watching for G here, and now when we hit x equals 2, now G starts chiming in. And it's negative, getting more negative, negative 2, negative 3, negative 4, negative 5, negative 6, and then we start over. So G didn't register anything here, but then when we got to 2, look what happens. It starts negative and gets more and more negative the whole way. So what might be function G?
Could it be the integral from 2 to x of our little f function?
Okay, she's offered up integral from 2 to x. And you want to use little f, okay? Little f of?
T.
And we could have used capital P too, right? So we know those are the same. What do the rest of you think? Does that make sense?
Yeah, that makes sense.
Yeah, because it started accumulating at 2, and then what happens to the signed area? We're accumulating at a negative rate, so we're just going to have the opposite of the accumulated area, getting more and more negative. So when we get to, so what does this negative 6.3 tells us? What about this gray region? What does the negative 6.3 tell us about the gray region there?
It's decreasing. Interval, f of n.
What is the area of that region?
6.3.
Positive 6.3, right? The area is positive 6.3, but our signed area is negative 6.3, right? So the actual area is 6.3, signed area is negative 6.3. So good. Okay, so let's look at H now. So let's watch what H does. So now H starts at 0, increases, now it's 1, now it's 2, now it's 3, and it's increasing. Now it's still going up. Now it's 4. Now it's 5. So it's been increasing the whole time, positive and increasing. What might the function h be? What's that about?
Is it
Unsigned area.
Someone's offered unsigned area. Starting from where? Starting from 1. So it's not this, because this what? This gives us signed area. We know that that was the function g, or we call it q from before. But now we're actually getting, and he said it, that's right, unsigned area, which is the same as total area, or just area. So unsigned area is always a positive value, and it's the area. It's the sum total of areas above plus the areas below the x-axis. So this function's not right. So what do I need to do to make this function right? How can I write this so it will actually give
absolute value sign.
Okay, where do
absolute value
you want to put that?
Around the f of t dt.
Okay, she's saying this. Does that do it? Yeah, because now whenever the function, the rate of change was positive, it'll still be positive and it'll accumulate area. But wherever the rate was negative, like now, in the gray region, it'll change that rate to be positive, and then it'll just keep increasing the area. Good. Okay, and then there's another way we can do this without absolute value. So how could we possibly do this without absolute value? I want to rewrite this unsigned area function, but I'm not allowed to use absolute value. What will that entail? What will that involve?
You can write it as 2 separate integrals.
I got to break this up, right? So if I'm going to use it without an absolute value, I got to break up this region. So let's write this out and see how we do. Here. So I've got it. All right, so it's what's called a piecewise function. So I'm going to do there we go. So I'm going to break it up into pieces. So what about in the first, for the first piece? For the first piece, I can just use the signed area function, right? Since it's always positive, I can just do the integral of f, right? So I'm going to do Control-Shift-I, and that's going to be from 1 to x of f, Control 9, f of t dt. And that's if what x is between, so 1 is less than or equal to x is less than or equal to 2, not 23. Okay, so we can use the same function from before. So what's going to change now is the second one. And now in the second one, I want to make sure that what I'm calculating by the second rule here is all of the accumulated area, all the way back starting from 1. So let's start with this part of it, though. So how am I going to get this part of the accumulated area? That's going to be the integral from, now starting from 2 to x. And now what does my rate need to be so that I have unsigned area, or area? What do I have?
Negative.
Right, I'm going to take the negative f, take the opposite of f, t dt. Now, but the thing about this is, it's only going to give me what? It's going to just, this so far will just give me the area of the gray region. Right, taking the opposite of the rate so that it makes that positive, and then accumulate from 2 up to there, that'll just accumulate that much positive area. but I want, so this is if 2 is less than x is less than or equal to 3. What do I want? I want this x, when I plug in x equals whatever this is, 2.24, I want to get all the accumulated area. So how do I need to change this?
You need to add the integral from 1 to 2 of f of t dt.
Exactly. I'm going to need to add all that accumulated area when x was 2 from before. And we could add an integral. That would work. We could add an integral, but there's a more kind of efficient way to do that.
Could we add the capital, like, f of, I forgot what, like, the original function's name was. But we add that.
Okay. Yes.
Instead of the whole
But
integral.
we can actually use this one. We can actually use the only, because we're at past x equals 2, we know what h of 2 is. So we can actually use h of 2. That's all the accumulated area up till 2. And then we're going to add the new accumulated area where that function was below the x-axis, where the rate was negative. And what does that look like? You notice? What does this, do you see what's happening there? What is that? What is that? That we've seen before. It's like what?
Exact total.
Yeah, it's like total, right? So it's like exact total accumulation. Right? All the area that we accumulated up from 1 to 2, so all the previously accumulated area, plus the so far accumulated amount starting at 2 up till x. And so that'll give me all the accumulated area starting from 1 up until x when we're in this interval here. Okay, does that make sense? So yeah, so the absolute value is a lot easier, but this is a really great exercise to practice thinking about accumulation, understanding signed area, and then using this form of total accumulation, right? All the area from before plus the new accumulated area. All right.
I just have a question.
Please.
If you were going to use the absolute value bars
Mhm.
in this function that you just drew,
Mhm.
so instead of having that negative sign in front of the f of t, you would just have the absolute value.
Yeah, I wrote that earlier, so it's really, it makes it really simple.
Gotcha.
It's
Thank you.
this thing. So this is the same function h that we just wrote without absolute value. So that's from 1 to x.
But you would still need that h of 2 to get that total accumulation, or
In this one,
oh, never mind. Nope, you wouldn't.
yeah, this takes care of it. This is perfect, right? Because this makes the function positive the whole way, and you just accumulate, starting from 1, just accumulate total area. Or
Okay.
you accumulate unsigned area, yeah.
Right.
But this is a really good exercise for understanding all the stuff we're talking about. Okay. Yikes, 3 minutes. Okay, so the next thing we're going to talk about is volume. So we've talked about using our accumulation functions, our integral accumulation functions, to work with area, and we see that if you just use the function value, you actually get a net accumulation of signed area, difference of areas, right? And so you actually have to work harder to get a true area function. To get a true unsigned area function, you have to work harder. Okay, and we've done that. And so now we talk about accumulation of volume. So if I want to write an accumulation of volume function, what do I need? What do I need to write an accumulation of volume function?
You need the function that would give you the area of the of the.
Okay.
I don't know, whatever.
So we have one vote for we need a function that gives area. And why What's your thinking behind that? Why do you need an area function to find the accumulation of volume? What's your thinking behind that?
I don't know. I guess then I don't know actually.
Okay.
Isn't area the derivative of volume? So the rate of change of the area is, or the derivative of volume is the rate of change of the area.
Okay, so you're talking about rate of change. That's good. So just in the kind of the most general sense, without getting into too much detail, if I want to find accumulation of volume function, what do I need? Uh-oh, did we all forget? So this is kind of a
Rate of change of volume.
rate of change of volume, right? So to write volume accumulation, we need the rate of change of volume. Okay, that's what we're going to work on next class. But let me just give you a preview of volume. So what we're going to do with these volumes is we're going to start with a curve here. So this is so this is like the XY plane, but we got a three-dimensional version of it. And so we're going to take a curve like this, and one way we can create volume is by rotating the curve. So if I came and I rotated that curve around the x-axis, it would create an empty shell. So I'll show you a side view here. So it's almost, the shell is almost done. So again, the x-axis is now coming out right out at you, y-axis is up, and we're going to rotate that curve around the x-axis and make an empty shell. And then after we make that empty shell, we're going to fill that shell as x increases. We're going to let x increase, and we're going to fill it with cylinders. We're going to fill it with cylinders and track the current accumulation of volume of those cylinders. And so that will be, accumulating the volume through this. And when x gets to here, the accumulated volume will be the volume of that solid, the whole solid. Does that make sense? So we got the empty shell. We're going to rotate the curve, make an empty shell. We're going to fill it with cylinders and keep track of the volume of those cylinders. And that's going to be our volume accumulation function. So what we're going to need is, based on those cylinders, we're going to need the rate of change of volume, right? So how those cylinders grow, at what rate do those cylinders inside grow? That's going to be the key, because that's going to be the rate of change of volume. Does it make sense?
So like the height of the cylinder would be the rate of change? Or what's the rate of change?
Yeah, we're going to develop that. So next class, we're going to work out what the rate of change is based on those cylinders growing through there. Cylinders are going to grow through there. And so based on how those cylinders grow, we're going to figure out what the rate of change of volume is.